Welcome to the third seminar in our series. This is Introduction to Confirmatory Factor Analysis in R with lavaan. My name is Johnny Lin. I am one of the consultants at the IDRE OR Statistical Consulting Group at UCLA. Just a little bit about my background. I got my Ph.D. in quantitative psychology here at UCLA as well. And during that time, I kind of focused on latent variable modeling, so including CFA and structural equation modeling. So that's kind of my training. And so that's what I'm going to be talking about today as well. So someone asked if the recording will be available. So we are working on processing the recordings a little bit faster, but it does take typically a month for us to upload it. So but here is where it's going to be uploaded to. The full link is here. Maybe I should put that in the, I think I put that in the chat, but I'll put it again. So this is our IDRE YouTube channel. It does include other departments within IDRE, but more specifically, you go on this playlist, you'll see the statistical consulting playlist. And currently there's only one video right now, but we're in the coming months, we'll be uploading all the previous videos pretty soon. It's just we have to work on closed captioning, so that's going to take a little bit. But otherwise, you're going to be able to find the playlist there. Okay, any questions about that? And during the seminar, just feel free to unmute yourself if you want to ask a question. Just make sure to re-mute yourself because sometimes we hear like background noise and that's kind of distracting. So just re-mute yourself every time, okay? The other thing is we have other consultants here. So Andy Lin is the supervisor of our group. So he will be moderating the chat along with Siavash Jalal. So if you have any questions that you don't want to ask over the microphone, you can put them in the chat. And then Andy and Siavash will be moderating it and answering your questions there, okay? For me personally, I don't have enough resources to go back and forth between the chat. So if you want to ask me a question directly, just unmute your microphone. And my name is Johnny Lin. Just call me Johnny. You can do that if you want. And all right, so the first thing you kind of want to do before we get started is really just to make sure you have the libraries installed in R. Make sure you have R and RStudio set up, and then load the packages, okay? You can download the code here, and then the slides. All right, the exercises we're gonna work on later. So how this is gonna work is I'm first gonna kind of do kind of a lecture style, but I wanna make it interactive, so I'm gonna include some polls, I'm gonna include some questions for you to answer. And then the second part, though, will kind of involve more like exercises for you to work on. Just I have 3 exercises set up, but if we just get to 2, that's fine. And it's more of a place for you to ask questions and interact. So, but throughout the seminar, feel free to ask questions at any time. It's just the first part is going to be a lecture format. The second part is going to be more of an interactive exercise format. Okay. And yeah, and then so do you guys have any questions so far about how the lecture is going to be set up? Okay, if not, we're going to go into the PowerPoint slide. So make sure you can click on that PowerPoint slide there. And I'm just going to share my screen there. So you should be able to see something that looks like this. Let me know if you don't see that. And this is where we're going to work off of for most of the presentation, okay? All right, so any questions before we start? Otherwise, we're just going to jump right into it. Yeah, and thanks, Andy, for including the link to the slide. So if you're here for confirmatory factor analysis in R, you're in the right place, okay? All right. So here's an outline of what we're going to be talking about. You know, the previous feedback I've got from other seminars is try to keep it kind of concise. Okay, so we're going to focus on very specific topics that are basically going to help you run your analysis in lavaan. All right, we're not going to go over every single like advanced topic in CFA. That's beyond the scope of this seminar. It's really just to get your hands wet in terms of the theory, and then in terms of how to run a CFA in lavaan. We're not going to go over like advanced topics like multi-group as CFA or something like that. So it's really just going to be very intro. As long as you kind of understand how to run the code and how to interpret the output, I think that's what we're going to accomplish today. So I like kind of, applying what I know to a data set. Okay, so instead of always just focusing on the theory, what we're going to do is kind of motivate this example with a fake data set called the SAQ, and I'll explain what that means. I come from a psychology background, so I'm very familiar with questionnaire and Likert type sales, and that's kind of where factor analysis came from too. We're going to talk briefly about the variance covariance matrix. So if you're not familiar with matrix algebra, it's just a kind of a way to kind of describe the CFA model. And it's a very important element of it. So I want all of us to understand that before we jump into CFA. And then the model itself, what a factor analysis model is. Okay, if you've taken regression before, then this is going to be kind of a bridge between regression and this. Then I'm going to talk about the model implied covariance matrix, which is basically how to recreate that variance covariance matrix using the model that I'm talking about here, the factor analysis model. And if matrices are kind of scary and unfamiliar, path diagram is going to help you because it's a way to visualize that. Okay. And in terms of getting straight into the CFA, you do have to kind of understand what are parameters, what are free parameters, what are degrees of freedom. It's a little technical, but bear with me because it really helps you to understand the concept of identification in CFA, which is important. So the basic CFA is a 3-item CFA. And how do you identify that? I'll talk about that later, because like basically you can't just run that CFA because you have something called a latent variable, which is a factor. So it's not like a regression where everything's identified. So you have to fix something to be identified in CFA, and I'll show you how to do that. And then I'll show you how to run that CFA in lavaan. So once you have a CFA, there are certain CFAs where you are able to assess, for example, how well the model fits. How well does your CFA fit? And that's using something called the chi-square, or you have other non-exact fit indices, which are called approximate fit indices. And I'll explain why we need that later. But there's the CFI, the TLI, and the Rmsea. And then finally, we'll just do a really brief example of a 2-factor CFA with correlated factors. Then we'll take a quick break, and then we'll go into exercises. Okay, so that's going to be the format of our seminar. But before we do that, I kind of want to start our first poll. It's not content related. It's just basically, I want to understand like how your kind of background, and if you've had experience with like linear regression and R, or if you've heard of like CFA or EFA or concepts like that. And if you don't mind taking just like 30 seconds to kind of answer that, that'll help me to target my seminar, or at least change the pace a little depending on your familiarity with these topics. All right, I'll give maybe like 10 more seconds for you to respond. 3, 2, and 1. Let's share the results. Okay, so you guys are, okay, some of you use R frequently or sometimes. Most of you use it sometimes. That's okay. Okay, so that's good. All of you have taken a course in linear. That's perfect, really, or most of you. And you've heard of CFA, but never learned it. Okay, awesome. And 40% of you have taken a workshop in CFA. That's good. Okay. All right, perfect. Thank you for answering that, by the way. That's actually really helpful. So that means I can kind of talk about concepts like the linear model, right? Like the regression model, or like the null hypothesis, maybe. All right, perfect. Okay, so we're gonna just introduce what CFA is, kind of. All right, so before you talk about CFA, though, you kind of have to see it in the broad context of just the latent variable models in general. So what I draw in the circle is basically what we call a latent variable, a set of latent variable models. Okay, there's other latent variable models besides this, but these are the main three ones. So there's EFA, there's CFA, and then there's SEM. EFA stands for Exploratory Factor Analysis. And by the way, the link underneath there is a link to one of my pages that I wrote. So you can click on that link if you want like a thorough treatment on the website for that topic. So EFA is called Exploratory Factor Analysis. And it is a latent variable model because the factor is unobserved. So this is more appropriate when you're just exploring a study and you have no idea how the items in your survey kind of relate to each other. So if you're developing a new depression inventory, okay, and you just collect kind of questions that you think are related to depression, but you don't know exactly if it measures depression, that would be appropriate for an EFA because you can use that to explore the structure of the survey. You can remove items, you can add items, you can use it to kind of figure out, is it a one factor, is it two factor? And that's kind of what I explained in the seminar there. CFA is if you already have a developed hypothesis. So if you already know that you have a depression inventory, like the Beck depression inventory, let's say, or CESD, these are popular psychology depression inventories. And you just kind of want to see how well this survey is conducted in your particular sample. You want to test the hypothesis that your sample kind of replicates the what we call the covariance structure of the Beck depression inventory. Then you would use CFA. So it's testing a particular hypothesis. There's actually a null hypothesis that you're trying to either refute or unrefute. Okay, so that's CFA. And SEM is kind of related to CFA in that it's a broader framework where it's not just factors analysis, but it's actually relating factors to each other. And I talk about that in my intro to SEM seminar. It's also in lavaan, but it's basically allowing you to run kind of regressions on the factors, where CFA only is concerned with what we call the measurement model. So in terms of software, traditionally too, it's kind of different. EFA traditionally has been a precursor to CFA. So EFA was developed before CFA. And so programs like SPSS, there's a function called SPSS factor that does EFA. But for example, SPSS itself does not do CFA. So recently they expanded kind of a package called AMIS, which was traditionally separate from SPSS, which does do CFA, but it looks very different from SPSS because it's not traditionally part of SPSS. So another example of a CFA package is called M+. That's a very powerful program. And I recommend if you're really into studying like CFA and SEM and you want to use that in your analysis, I highly recommend considering M+ beyond lavaan if it's beyond a basic analysis. M+ is very powerful. And speaking of M+, then M+ also does SEM. Okay, so SEM and CFA kind of go hand in hand. So like I would kind of group SEM and CFA together, and then EFA is kind of its separate own entity. Okay, so EFA is more exploratory, like the name implies, and CFA and SEM are more confirmatory. Any questions about kind of what the conceptual difference is between EFA, CFA? All right, so today we're going to be talking about CFA. Okay, so to motivate the example, we're going to talk about the SPSS anxiety questionnaire. So maybe for some people, they are scared of using statistical packages like SPSS. So this is just an example of 8 items from the SAQ. And for example, statistics makes me cry. You know, like for me, statistics makes me happy, right? But for some people, it makes them cry. So these are example items from the survey, and we hypothetically collected 2,571 people for this particular sample. And for each of these items, they are scaled in what we call a Likert type scale, going from strongly disagree to strongly agree, 1 to 5. Okay, so that's, some people ask like, okay, can I do kind of regression or CFA on Likert scales? Yes, just know that you know, ideally it should be kind of normally distributed. And if it's not normal, then you have to consider other kind of non-normal adjustments to your CFA or SEM, but we won't talk about that in this seminar. That's more of an advanced topic. Okay, but I would say this is a good one because it has 5 categories. Now, it wouldn't be as appropriate if you just had like 0 or 1, like yes or no. That's something called item factor analysis, where you have to kind of look at kind of a logistic regression for that. Okay, but otherwise you can treat this as a continuous or ordinal scale. Okay. So like I said, like before we start the seminar, if you want to be part of the exercise portion of this class, you'd want to install these 2 packages. The reason why we want the foreign package is because I want to download this SPSS data set. You'll notice the data set is an SPSS data set called SAV, SAQ.SAV, and foreign converts that to a R data set. But primarily you want to work with lavaan, which is going to be the CFA or SEM package that we're going to be talking about today. And if you're able to use this command to download the data set, then you're good to go for the exercises. Okay, so, but we're not going to get into the exercises for now. We're going to be mostly talking about kind of the lavaan syntax and the output, and then we're going to go into exercises after the intermission. Okay, but before we jump into factor analysis, I kind of wanted to just review concepts of the covariance or correlation matrix, okay, because that's important for understanding factor analysis. So basically, factor analysis is looking at the correlations among items, right? So what you want to consider is basically how well do these items correlate, and then across all of them, how well in general do they correlate? Okay, because factor analysis kind of reduces the dimension of your items down to just 1 or 2. Let's say you have 1 or 2 factors, and you want to make sure then that all the items are interrelated with each other. Because if you think that these 8 items are measuring SPSS anxiety, they should all be generally correlated. And if some of them are not correlated, you have to question whether it really measures SPSS anxiety, right? Because maybe it's just measuring something else. So the first thing you'll notice is that there is a 1 on the diagonal of this matrix. We call this a diagonal of this matrix, but that's because you know, everything correlates with itself perfectly, right? So remember, a correlation ranges between -1 and 1. Okay, so 1 just means it's perfectly correlated. All right, so the other thing to note is, what is the correlation on the off diagonal? So that was the diagonal. Now this is an element in the off diagonal, right? So what does that mean? This is the correlation of item 1 with item 2. And let's see what item 1 was. Item 1 was statistics makes me cry. And then item 2 was my friends will think I'm stupid for not being able to cope with SPSS. So you notice that that's a negative correlation, but it's kind of low, okay? So that means item 1 and item 2 are negatively correlated. Now, what about item 2 and item 1? Okay, so we looked at item 1 and item 2, which is here. What about item 2 and item 1? Well, you notice it's the same correlation, right? So correlations are symmetric, meaning like basically 1 and 2 is the same as 2 and 1. So is that true for everything? Yes. Well, if you look at 3 and 1, it's the same as 1 and 3 is the same as 3 and 1, right? So if you go through all the list of symmetry, you'll basically find that there's something called the upper triangle here. And then there's something called the lower triangle. So I'm drawing two triangles. And I claim that the upper triangle is exactly the same as the lower triangle. Right? And you can verify if that's true, prove me wrong if I'm not. This is a property called symmetry, right? Like I said. So what's the benefit of having symmetry? Well, because if you estimate 3 and 1, the correlation, you don't have to estimate 1 and 3, right? So that reduces the number of parameters. Okay, it saves you some estimation. And if you were a computer, you like that because then you can literally just do 1 and then you get 2 for 1. So that's a good property to have, is that this covariance matrix is symmetric. Okay, or this correlation matrix. The other thing you have to kind of just note is that this is a correlation matrix. SCM, however, or not SCM, CFA and SCM uses what we call the covariance matrix. Okay, so how do you know the difference between a correlation and covariance matrix? Well, you basically see that the diagonals are no longer 1. If these you see are no longer 1, then you know it's a covariance matrix, because then it's not in the correlation metric, because correlation, remember, is a standardized covariance. So right now we're looking at a correlation matrix, not a covariance matrix. Okay, any questions about that? All right, so this is where we get into a little bit of linear equations. And if this is a little scary to you, don't worry, we're just gonna kind of gloss over it, and then you don't really have to know the technical details of it to understand CFA. But since most of you have taken regression, you probably have seen this linear equation before. This is basically a linear regression, right? So you have your outcome, your dependent variable, you have your intercept, you have your slope, okay, and then you have your predictor, and then your residual. Well, CFA isn't that different from a linear regression. You have an outcome, which is your item. Let's say it's statistics makes me cry. That's your item. You have an intercept. That's called tau 1. You have a coefficient or slope, kind of. You can call it a slope, but basically called a loading. This in CFA is called a loading, but it is a coefficient. And then the eta, what is eta? This is the predictor, right? But this is actually the factor, okay? So instead of being called a predictor, it's just the factor. And what's so unique about the factor? It's unobserved, okay? So what's the difference then between linear regression and factor analysis is that the factor is unobserved, but the predictor in linear regression is observed, okay? So that's the main difference. And then you also have kind of a residual term here. So why did I put a 1 here? Well, the 1 is saying kind of, this is a multivariate equation. Okay, and this is a univariate. Multivariate means I have multiple outcomes. And what are my multiple outcomes? I have 8, remember? I have statistics makes me cry. My friends will think I'm stupid for not being able to cope with SPSS. Standard deviations excite me. Those are the first 3 outcomes, right? Each of those has a separate intercept, a separate loading, separate residuals, but what do they have in common? They have a single factor in common. Why is that important? Because we're trying to say that this single factor is the predictor of all 3 items. They correlate because of this factor called SPSS anxiety. Does that make sense? And if you write out, this is called the matrix formulation. If you just write it out in terms of equations, you'll see that it's just 3 separate equations, basically 3 separate regressions with the same unobserved predictor or factor. Any questions about that? Yeah, and so just FYI, like this is the more theoretical part, but I promise we'll get into the lavaan part later, okay? But I feel like this is important for you to at least understand why we do CFA. Okay, so now that we kind of know the covariance matrix and then the the factor model, basically, this is the covariance matrix. And then this is the model implied covariance matrix. Just know that the covariance matrix comes from the data. And then this model implied covariance matrix comes from your model, as it states. So how is this different from what I showed you before? Well, first thing I showed you before was a correlation table. That came from our data. This comes from the population. So that's what you have to keep in mind is that the upper Greek letters mean population. So these are in the population, not in my sample. And how do I get this model covariance matrix? Well, I show it in the appendix in the web page, but basically it comes from that lambda. Remember that lambda coefficient? If I take the covariance of that factor model, I'm going to get that lambda. This is the covariance of the factor. And then this is the covariance of the residual. Okay. So again, I write it out here. This is the lambda. This is the covariance of the factor. Or actually, it's the variance, right? Because the covariance of itself is variance. And then multiplied by the loading. And then this is the residual covariance. This is what's left over, that epsilon, remember? That I take, this is, for example, the variance of the 3 residuals. And then these are the covariances. And remember, this is also symmetric, so I don't have to estimate these. Okay, any questions about that? All right, so if that was scary, then basically I have a picture for you to look at, okay? Pictures to me are less scary than equations, but the beautiful thing about a path diagram is that you're able to map the equations to these pictures. So before we do that, though, we kind of have to understand the elements of each path diagram, right? So the element that you're probably most familiar with if you've heard of linear regression is this one. All right, this is the observed indicator. This is your observed outcome, your dependent variable that you use in regression. Now, what you may have not seen before is the latent variable. Okay, so this is F, or what I can call eta, remember that? So this is a factor, right? It's unobserved. So circle means unobserved and square means observed. Triangle means intercept. So remember the tau that we had, or we had the beta is not, you can call it whatever you want. That's the intercept term. And then this is a path, right? So what goes in here? So this could be your beta 1, right? Or it could be your lambda, right? That's your path. And then this is a variance. If that's one arrow. If you have 2 arrows, it's called the variance or covariance. So remember, what was one of our variances? That was the psi, right? That's the variance of the factor. So those are the basic elements of the path diagram. And then if you wanted to kind of see how it works, so this double arrow means variance, right? And the circle means factor, right? So the variance of the factor is psi 1, 1. The factor is eta. Now the eta predicts the outcome 1, right? And that's the loading. Any questions about that? How to translate the equation to path diagrams? Let's see if there's, okay, good. You guys are asking questions on chat, that's good. Feel free to unmute your mic too. Okay. So what I mean by, so all of these are measurement models, okay? So what I like to do is kind of think about, okay, which part of it is coming from the factor model, and then which part of it is coming from the covariance model. They're the same model though, okay? So they're both the measurement models. I just wanted to clarify that. But if you kind of go through this path diagram, okay? So first, let's look at the dependent variable. Right, so this is basically statistics makes me cry. What else? My friends will think I'm stupid for not being able to cope with SPSS. And then standard deviations exciting, for example. Okay, so those are your outcomes, right? They're observed. That's why they have a square. Now, what's predicting the outcome? The latent variable. That's the factor, right? Eta 1. How many factors do I have here? 1. I only see one circle, but I have 3 outcomes. Okay. So what is the regression path from the factor to the outcome? These are the loadings. I have 3 loadings. Right. So that I just checked those off. Those are in the factor model equation. Right. What's left? Well, I have the intercept. Tau 1, tau 2, and tau 3. Those are unique to every item. Every item has a unique intercept. What does this 1 mean? If you know regression, basically it's that column matrix, the design matrix of X, where you have the first column being the of X being the intercept. Okay, that's where it comes from, that 1. It's part of the design matrix. And then you have finally the residuals, right? The error terms here. All right, so those come from the factor model. Now that's in green, right? But remember, we have another equation, which is the covariance equation. And there I have what terms? Well, I already have the loadings, so I don't need those. But I do have these, right? That is what? What is that? That's the factor variance, right? Where does that come in? Well, that's the double arrow, remember, of the factor, which is a circle. That's called the factor variance. That's the factor variance of eta 1, which is the first factor. That's the SPSS anxiety factor, right? Okay. What's left in blue? We have the covariance of the residuals, that covariance matrix. Well, what did I say here then? Remember that the diagonals are the variances. So I have 3 variances of the residuals, 1, 2, and 3. What does it mean when I have 0 on the off diagonal? And remember, it's symmetric, so the upper triangle is the same as the lower triangle. When I say 0 in the off diagonal, this is the covariance of item 2 and item 1, right? So what I'm saying is that covariance is 0. I'm also saying the covariance of 3 and 1 is 0, and 2 and 3 are 0. Now, what would happen if I didn't set those to 0? How would I draw that path if I didn't set those to 0 and I allowed the covariance? Do you guys have an idea?
Would you just put arrows between epsilon 1 and epsilon 2 and so on and so forth?
Exactly. Great. Yes. So you would draw a double path, right, between these. Right. Perfect. So that would be theta 1, 2, theta 2, 3, and I'm missing one more, right? So that's how you would draw what we call a correlated error model. Perfect. Good job. All right. So do you guys understand basically how to translate the path notation to your linear equation? And more specifically too, is which parts are the covariances and which parts are coming from the factor model itself. Because I for the longest time when I tried to learn this, I was like, how come some of them are like covariances and some of them are just like terms? Well, the point is that they come from different kind of equations, okay? That's why I kind of wanted to separate these out in colors. But all of this is called a measurement model. And that is distinguished from the structural equation model or the structural model, okay? Which we won't talk about here, okay? But I'm just laying it out, okay? Structural. But basically, we are only talking about the measurement model, and that means a model that relates latent to observed variables, right? Latent to observed variables. It's basically how well our measure is being measured. Our survey is being measured. Okay, that's why it's called a measurement model. Just think about measurement in terms of like a ruler, right? if we have height, it's relatively easy to measure with a ruler. Think about a concept like in psychology, like depression. How difficult is it to measure depression? It's pretty difficult, right? Like, you know, human behavior is very difficult to measure. And that's why we need measurement models, because we need to assess how well our construct is being measured. It's not like physics where you can kind of just measure the speed of light. Okay, there's going to be a lot of error involved in that measurement, and that's why we have these errors. Any questions about these concepts that we've been talking about?
I have a quick question.
Yeah.
How do you decide whether to go for a correlated error model or not?
That's a good question. And I see that often. The question is basically like, okay, when do you add these correlated errors? Honestly, the point is not to add them if you don't have to, okay? Because what I see that happens a lot is people, if we're going to talk about model fit, but they look at the model fit and they're like, oh, it looks terrible, so I'm going to try to improve my model fit. And by adding more covariances of the residuals, it artificially inflates the model fit. I don't like that, because that's basically kind of like confirmation bias. It's saying, I want this model to fit, and I'm going to force it to fit by allowing these to covary. Why does it fit better? Because obviously the more things you add, the better the fit, right? It's kind of like linear regression. The more predictors you add, the better your R squared. I argue that that's artificially improving the fit of your model without a strong hypothesis. The only context where I've seen that it actually makes sense is for, and we won't go over this because this is a more advanced topic, is if you have, like, let's say husband and wives, okay? So I've seen that before, like a husband depression and a wife's depression. Like basically because husband and wives live so closely together, maybe if the wife is depressed, the husband would be depressed too, right? Just because they're kind of like correlated. So in that case, then maybe I would correlate the error of husband and wives. Okay, because what you're saying is that, okay, so not only, this is like depression, not only is it just depression that's accounting for the covariance between husband and wives, but it's something else. It's just the fact that they're just living together, right? And maybe like there's random factors from living together that makes them depressed, not just depression itself. Okay, does that answer your question?
Yes, thank you.
Yeah. Yeah, so in general, don't do correlated errors if you don't have a strong hypothesis about that. Any other questions? All right, if you don't have any questions, that was kind of like the theory about the factor analysis model. Now we're going to jump into kind of like one factor CFA, but before we do that, we have to do something called degrees of freedom. And this is a little technical, bear with me, but I promise it'll help you understand why we're doing it, okay? And then we're going to talk about an actual one factor CFA. Okay, so this is basically what we're trying to do. We're trying to fit one factor CFA with those just 3 items that we have in the SAQ. Let's see if I can find. Okay, so item 3, for example, is standard deviations excite me. Item 4 is I dream that Pearson is attacking me with correlation coefficients. So I have nightmares about correlations. And number 5 is I don't understand statistics. So what you're saying is then, okay, I'm assuming that those 3 items adequately assess SPSS anxiety. I don't know if that's true, but that's my theoretical kind of idea before going in to my factor analysis. This is, I have an idea that 3 items is sufficient. Okay, so that's the CFA we're trying to fit. Before we do that though, we have to know like whether or not we can fit a CFA. And to do that, we have to talk about degrees of freedom. Okay. But degrees of freedom comes with some other things that we have to go over. So we've seen these before, right? We've seen these before. We've seen this population covariance matrix, right? Remember, it's symmetric, right? We've seen this model implied covariance matrix. We haven't seen this one yet. Well, this is actually what I was showing you before. This is called the sample covariance matrix. Okay. And the sample covariance matrix is an estimate of the population. So it's an estimate of this. That's why you have a hat there. This is called estimate. That's an estimate of the population covariance matrix. Basically, I'm using my data to recreate the sample covariance, the population covariance matrix using the sample data. So how do I know, first of all, that this is a covariance matrix? Well, you look at the diagonal and they're not one. Second tip off is I'm using COV and not COR in R. Okay. And I also know that it's symmetric. So it maintains the properties of the population covariance matrix. It's just that these are sample estimates. Okay. So we got that out of the way, right? Now, in terms of degrees of freedom, okay, what we want to look at is the number of terms in the population covariance matrix. Using the sample covariance matrix, though, we can do the same thing because the properties of the sample covariance matrix are the same, right? So as the population, in terms of the number of elements in that matrix. So if we have a 3 by 3, this is a 3 by 3, 3 items by 3 items, we have 9 elements, right? It's the same 9 elements in the sample covariance matrix. Well, how many elements do we have then? Well, instead of counting it one by one, there's a little trick I can use. It's just say, I want to multiply the number of items times the number of items plus 1 divided by 2. So for a 3 item CFA, I have 3 items times 3 plus 1, which is 4, divided by 2, which is 12 divided by 2, which is 6, right? Why is it 6 and not 9? You guys have any idea? I kind of talked about this before. Yeah, go ahead.
Because the matrix is symmetric.
Yes, perfect. Okay, so basically, just like you said, is you notice these are the same as this. This is the same as this. Okay, so you get my point, right? Yes, it's symmetric, so you don't have to duplicate that, right? That's perfect. So just counting the number, right? Then you have 1, 2, 3, 4, 5, 6. Okay, perfect. All right, so, but that's not like the number of parameters, right? That's the total number you have to work with. Those are what we call known values. I think I saw that in a term somewhere, a book somewhere, and then I just stuck with it. So those are the total number you have to work with. Now, if my model parameters exceed that total 6, I can't estimate the CFA. So let's look at our model implied covariance matrix. Remember, we talked about the model implied. We have our loadings, right? We have our we have the variance of the factor, and then we have the variance of the residuals. How many do we count? Now, count the unique ones, right? Okay. So let's say we didn't constrain the residual. Okay, so let's count it. 1, 2, 3, 4. I have this one, I have this one, I have this one. And then I have 9 here, right? Well, not really, right? But we have 6 because they're symmetric. Okay, so 6 plus 4 is 10. Okay, you see how I got 10? Now, even though I counted the non-unique ones, like I canceled these ones and I canceled these ones, that's not enough still. We have 6 to work with, but we actually have 10. So how can we do that? Well, we have to do something called fixing a parameter. Fixing a parameter just means I want to predetermine the parameter to have a specified value. This is not realistic, but it's just a very easy example of saying, how about we just fix everything to 1s and 0s? You can do that, right? Well, you can, it just doesn't make sense. But let's say we fix the loadings to 1. We fix the variance of the factor to 1. We fix the variance of the residuals to 1, and then the covariances to 0. Well, how many have we fixed there? We fixed Well, I mean, like unique ones, right? We fixed 10 unique ones, right? Okay. So, so the number of unique parameters minus the number of fixed parameters is what we call the number of free parameters. So in terms of our number of unique parameters, we had 10 and we fixed 10, right? So 10 minus 10 is 0. This is a very arbitrary, like non-realistic example. So how many number of free parameters we have? 0. Well, then the degree of freedom is the number of known values minus the number of free parameters, just 6, okay? And realistically, you will never get 0 as a number of free parameters. I'm just showing you an example of an extreme case. So we count at 6, right? Now, what does that mean for our model? Well, you have 3 cases. In our case, our degree of freedom was positive. That means the number of known values is greater than the number of free parameters. This is called an over-identified model. The benefit of having an over-identified model in SCFA or SEM is that model fit can be assessed. We can talk about model fit when we have an over-identified model. Well, let's look at the other extreme case where DF is negative. That means the number of known values is less than. So let's say we had 5 and then we had 6. Then we get a degree of freedom of -1. That can never happen. That's called under-identified. You cannot run a CFA, that model that is under-identified. You will never see degree of freedom negative in your output. If you see that, tell me and I'll buy you a house in Laguna Hills. All right, so that will never happen. Now, then if you, the kind of just right scenario is when the degree of freedom equals 0, and that means the number of known values is equal to the number of free parameters. Let's say we had 6 minus 6. That happens actually a lot. If you guys know, actually, linear regression is a case where the degree of freedom is 0. You have no degrees of freedom to work with. And that's called a just identified or saturated model. That's okay. You can have these models. Linear regression is a perfect example of that, but it's just you can't assess the model fit. The fit is as good as it can be. Okay. In CFA or SEM, we want to be able to assess model fit. So you want to be able to over-identify your model, meaning you want the degree of freedom to be positive. Any questions about degree of freedom? I know it's kind of technical, but basically just look at the degree of freedom and see if it's positive. And then if you see it's 0, then you know why you can't assess model fit. This is a good time to kind of test your knowledge. So I'm going to administer the next poll. See if you kind of got an understanding of what I was saying. And this will help you to understand too. If you get it wrong, then you can kind of think about, okay, what was I misunderstanding? So it's in the slides. It's also in the poll. And basically, the first question is, there's 1 degree of freedom in my model, which means that my model is over-identified, true or false. The second question, I have 3 items in my study. The number of known values is 6. And third question, I have 3 items in my study. There are 6 unique parameters and no fixed parameters. My model is just identified. The last one may be kind of tricky. Yeah, and we're going to go over the last one for sure. And then you tell me if I'm right or wrong. And feel free to refer to the slides before, because the last one especially, you kind of have to look at that equation again. So for the third one, just if you're still kind of answering that, think about how many free parameters you have. Maybe I'll give you guys like 30 more seconds if you're still thinking. Okay. Maybe 10 more seconds. And don't worry if you don't have a response yet, we'll just go over it and you can kind of see, at least you thought about it. I think that's the most important thing, is to kind of think about the question and see if you understand it. Okay, so let's look at this. So the first one is there's 1 degree of freedom in my model, which means that my model is over-identified. That is true, right? Because if the degree of freedom is positive, that means you have an over-identified model. So you guys, most of you got that right. Good job. I have 3 items in my study. The number of known values is 6. That's true because remember that formula we had, P times P plus 1 divided by 2. So those were kind of straightforward. The third one, maybe I tricked you or something because, and you tell me if I'm right or wrong, because maybe I missed something. But let me stop share. Okay. So it says I have 3 items in my study. So first of all, I know from 2 that the number of known values is 6, right? Okay. Now it says there are 6 unique parameters and no fixed parameters, right? So remember the number of free parameters is equal to the number of unique parameters minus the number of fixed. So what is that? 6 minus 0 equals 6. And then the degree of freedom is the number of known values minus the number of free. So what is that? 6 minus 6 is 0. And when my degree of freedom is 0, what is that? Just identify. Does that make sense? Were you guys like kind of confused about something maybe? Or if I did something wrong, you tell me. No? No questions about that? All right. Okay, so that's just to get you thinking about degrees of freedom. Really, like it's just a small part of your output, but you really need to know degrees of freedom to be able to identify your CFA. So here's our 3-item CFA. We're going to get into actually working with our CFA. Okay, so now you know all the kind of theory behind how to identify a CFA. Okay, so this is the exact same path diagram I drew before, right? We're just going to fit this now in lavaan. But if you calculate this, the number of degree of freedom of this model, I'm not going to do it here, but if you do the homework and you calculate it, I guarantee you it's not going to be identified. It's going to be under-identified because you'll have more parameters than you have known values. The degree of freedom is going to be negative, okay? Now, what I argue without proving anything is that it's going to be exactly 1 parameter that's under-identified. So what are some ways you think we can kind of resolve that issue? Do you guys have any ideas now that you know all the concepts now? Do you have any ideas about how we can reduce that identification problem?
Maybe we can fix the parameters, setting some parameters.
Yeah, good. Okay, so that's one way we can fix the variance. What about, is there another way?
Fixing the residuals.
Okay, that's a good idea. Now, typically we want to keep the residuals as it is because we want to know if there's error in our measurement. Okay, so we don't want to fix those. So but that's a good suggestion.
Can you fix one of the factor loadings?
Yes, we can choose one of the factor loadings to fix the one. Okay, so that's really good. Okay, the intercepts we usually want to keep as is, and the residuals you want to keep as is. And feel free to keep answering. And even if you don't get it exactly right, I think it's great that you're volunteering, and I highly encourage that. And it actually helps you to kind of sink what we learn into your brain, because you're like, oh, I got that wrong. I'm going to remember that for the rest of my life. Okay. Because that's me. Like when I hear negative things and then it's like, oh, okay, I'm going to remember that forever. Okay. So feel free to keep doing that. And I'm not going to judge you, because this is very difficult material to cover in just like 3 hours. Okay. So you guys are doing a great job understanding. Okay. So like some of us were saying, we can choose 2 ways to identify this model. We can either fix the loading or we can fix the variance. Okay. So how do we fix loading? Basically, we just set one of them to 1. Can you set it to 5? Yeah, you can, but that's not really useful, because you want to set basically the loading to be the scale that you want it to be. So what does that mean though when we set the loading to 1? That just means that we set the scale to that loading, or to that item. So the item is, let's see, what's the first item? I'm looking at the SIQ. Statistics makes me cry. So what you're saying by fixing the first loading is that I want to set the scale of everything else to be statistics makes me cry. So let's say you have a mix and match kind of a survey, or even just like a set of dependent variables that is like inches and height. You're going to be setting one of it to inches, right? And otherwise, if it's height, then you're going to be setting it to height. Does that necessarily make sense? No. Okay, so you have to think about when you do a marker method, you want to make sure that your items are all measured on the same scale. If that's not true, then you have to either standardize your scale first and then do marker method, or you have to standardize it using the variance standardization method. Okay, by default though, lavaan specifies the marker method, which means fix the first loading to 1. Can we fix the second loading to 1 and free the first one? Of course. Can we do the third one? Yes. But by default, it sets the first one. So just make sure you know what your first one is, and if you're okay with setting the scale to that item. The other thing is it sets the, by doing that, it sets the factor variance to that scale as well. Okay, so when you're talking about the variance of that factor, you're talking about it in the units of this statistics makes me cry item. Everything else we leave the same though, right? Okay, well, we leave it as a parameter, a free parameter. Now, like we said before, also, there's a second way is to standardize the variance. So recall that the psi is the variance of the factor, remember? Okay, so I just draw the path diagram here. That's the variance of the factor. We're going to set that to 1 for the variance standardization method. You see, so we put that in 1. Now, what do we do with the loading? We freely estimate. It becomes a free parameter. Okay, so that's basically the 2 methods of standardization. And if you calculate it out, the degrees of freedom, I argue that it's going to be 0. Okay, so before we get into how to do that lavaan though, which is kind of what the goal of this seminar is, we kind of want to understand this cheat sheet kind of syntax of lavaan. So you guys, most of you have worked with R before, maybe not lavaan, but you've done linear regression. So I'm pretty sure you're familiar with the syntax LM y tilde x, right? Where y is your dependent variable and then x is your independent variable. You guys know that notation, right? Well, it's the same notation in lavaan. When you have an observed variable predicting an observed outcome, you basically use the same syntax. Now, the thing with lavaan though is it doesn't estimate the intercept by default. So unlike LM that estimates the intercept, lavaan doesn't estimate the intercept by default. So in order to estimate the intercept, you have to do like y tilde 1 plus x. So if you do y tilde x in lavaan, it's not going to estimate the intercept. Okay, so just making sure you know that. Now, lavaan goes beyond linear regression, right? Because it allows unobserved latent factor. So this is where this equal tilde comes in. Well, the equal tilde is basically saying I want a measurement model. I want to link an observed to a unobserved to observed. So I want to link eta to y1. The only difference is that you need to split the side. So like, let's call the eta f. Okay, so you need to say something like f equals tilde y1. Okay, so that the sides are flipped. But that doesn't mean that f is an outcome. Okay, so don't get that confused. If you want to do that, that's called a formative construct, which we're not going to go over. But a lot of people come into stat consulting and they kind of draw the arrows the wrong way. Sometimes I even get confused, right? But you're not doing this. This is not what we're talking about, okay? This is not it. Okay, we're talking about this. So again, this is called formative. I think it's called formative, or it's called causal indicator. And then this is kind of the one we want to talk about, which is that the factor causes the items. Okay. So don't get the direction confused of which side goes into what side. Double tilde means I want a covariance. Okay. So now what does it mean when I say I want f tilde tilde f? Where f is like the factor.
The variance of the factor?
Yes, exactly. So the covariance of an item with its, or a factor with itself is the variance, right? Perfect. And in that case, we called it psi11, right? So really good job. Okay. And then 1 star fixes the parameter. Okay, so let me clear my screen there. So if I want, let's say I have this factor and I go equal tilde, right? And then I have y1 plus y2 plus y3. 1 star fixes the first loading to 1. Now, what did I say before is that this is the default in lavaan, so I actually don't need to do that, right? And I'll show you how to like override that later, but you basically use this thing called NA star, okay? So when I put NA star here, that basically unconstrains the loading, not to 1. So it frees up the parameter. That's called a free parameter, okay? We won't talk about variable labels because our value labels, because that's not important for this seminar. But do you guys kind of understand now the syntax of lavaan? These are basically the things you need to know, essential things you need to know for running a CFA. Oops. But otherwise, I think you guys are understanding this pretty well, so good job. Okay, now we are finally getting into lavaan. Okay, so basically what we want to run, remember, is a 1-factor CFA with 3 items. And I argue that this is a just identified model. Oops. So here's basically all the things we've talked about, and now into one little syntax here. You know, honestly, the syntax is not that hard. It's really understanding how to implement the syntax, what lavaan is doing, and how to interpret the output. That's really what's hard about CFA or SEM. We've seen this before, right? We know exactly what that means now. This is item 3, item 4, and item 5 in the SAQ. So if you keep referring to that beginning slide, then basically, let's see, where is it? Statistics makes me cry. I keep losing that one. Yeah, statistics makes me, no, that's the first one. So the third one is standard deviations excite me. The fourth one is I dream that Pearson is attacking me with correlation coefficients, and 5 is I don't understand statistics. So I just chose these because I didn't want, like, I think I looked at the loadings and like some of them were kind of off. So I just chose like these 3. But remember, this is saying those 3 items measure SPSS anxiety, which may or not hold, and that's why we're testing the hypothesis. Now, why do I have these single quotes? That just means it's a string. Okay, so like this means it's a string. So it's not a number. Why does it need a string? Because we're going to store that string into an object called model 1A M1A. And then I'm going to pass it into M1A, that string, into confirmatory factor analysis in lavaan. So it's called CFA. And basically, this is a wrapper, or it's basically like a proxy for the actual function in lavaan, which is actually just lavaan. Okay. But the reason why you want CFA is because like it's designed for CFA, so it'll tell you when it's like something's off. Okay. And you specify the model incorrectly. So this is good if you just want to run a CFA instead of using the lavaan function. And then this is the data set we're using. Why do I draw an arrow here? Well, this says I want to store that lavaan CFA output into this object called 1fact3 items A. And then I pass that object into summary, and then this is how I get the output. Any questions about the syntax of lavaan? And during the exercises, we're going to actually like kind of interact with this and like really like get into it. But for now, like, just trust me that this is the syntax. And then if I'm wrong, you can correct me later when you actually run it. Okay. But any questions about the setup of this syntax? It's pretty straightforward, right? And if you use regression before, it's kind of like regression where you pass on the object here, and then you put in the summary. The only additional thing is the string, because it requires you to have a string of the model. Okay, so remember there's 2 ways to identify the CFA, right? And why do I just show you this one first? Well, like I said, let me go back to the syntax. Like I said, by default, lavaan does marker method, right? So I didn't have to say anything here. This is where the theory comes into play, because if you didn't know that that's marker method, you would not know what lavaan is doing. What lavaan is doing is it's fixing the first loading in 1. And then it's unconstraining the variance. Okay, so it's really adding a 1 star in front of Q03. Let's see if that's true. Well, this is a summary output, right? And then I have the estimate column. This is where you check and verify that what you did was right. How do I know that the marker method was implemented? Well, in Q, go ahead. Anyone want to say something? Okay. But how do I know that I was using marker method? Well, basically I see a 1 here. How do I know that that's not actually an estimate? Well, there's no standard error, there's no Z value, and there's no probability. That's how I know that that's a fixed parameter, right? This is a fixed parameter. Now, all these other ones are free. You know that commercial that is a free, free, free. So these are all free now. Free just means it's estimated. Okay. So what is this now? These are the loadings. These are the lambdas, right? Lambda 1, lambda 2, let's say. These are the loadings of item 2, or item 4, and item 5. The thing is, though, since you scale these in the units of item 3, which is standard deviations excite me, these are in the units of item 3 now. Okay, so let's try to see if we can interpret one of them. So for, let's see, I think what I meant was item 4. So change that to item 4. So for a 1 unit increase in item 4, or sorry, in SPSS anxiety. Okay. Oh yeah, that's what I meant. So when I said item 3, I meant in the scale of item 3. So for 1 unit increase in SPSS anxiety, because remember SPSS anxiety is our predictor right here. And if you've interpreted regression coefficients, it's kind of the same thing, right? So for 1 unit increase in the predictor, it leads to a blank unit increase in your outcome. So for a 1 unit increase in SPSS anxiety, item 4 goes down by 1.13 points. That's in the scale of item 3 though, okay? In the scale of item 3. So is it easy to interpret? Not necessarily. Now the variance of the factor right here is scaled by units of item 3 now. Okay, so that is the variance of item 3, or the factor in scale of item 3. These are the residuals variances of item 3, 4, and 5, and I know that because there's a dot in front of it. Dot means residual. Now you can look at the p-value, but honestly, all that is testing is that the coefficient is greater than 0, which I don't know if that's that interesting in terms of a loading. Okay, and then basically what I did was I represented each of those parameters into the path diagram. And so you see that, this is a marker method because I'm fixing the loading of the first item to 1. All right, and I interpret these for you. So any questions about the interpretation?
I have a quick question about the
Yeah.
model.
Yes.
Why didn't we specify a y-intercept?
That's a good question. Okay, so yes, in the other diagram I drew this, right? And that is because of tradition. Okay. And basically SC or factor analysis or SCM came from the tradition of only having your covariance matrix. Okay, so your S. Okay, so in older programs like from the 90s, there's a program my advisor created called EQS. There's also something called LISROL. The first programs in SCM or CFA only have the covariance matrix. Okay, so the only input of your data was a covariance or a correlation matrix. All right, so by default in tradition, means aren't estimated. It's only because I think back then like computer memory wasn't available. So, or they didn't collect the data. Now we have the full data available so we can estimate the intercepts, right? So but for some reason, by default, the packages still don't estimate. A lot of packages don't estimate the intercept. But remember, we are able to get that, right? So what do we have to add to this syntax to get the intercept? One plus, right? So you can try that on your own. Is if you add 1 plus, you're going to get the intercept. Okay, and but just see, this is why you need to understand the theory and the specification of the syntax, what lavaan is actually doing. Because if you just put it in there, you're like, oh, this is the output, right? But you don't know, for example, then that the default is not to estimate the intercepts. So that's why you need to add a 1 plus. Okay, so that's a good question. Any other questions? Okay, this is where you have to kind of pay it. I mean, you guys are definitely paying attention, but this is kind of like, you kind of have to think a little bit. It's not just like, okay, I can look at the syntax and understand it. Okay, so remember that NA is what we needed to free the parameter. And then 1 star fixes the parameter to 1. So what is this doing? Actually, I think you guys have the tools to understand what this is doing. Okay, does anyone want to volunteer? If not, it's okay, I can go over it. But I think you have the tools to understand what this is doing. No brave volunteers? It is kind of challenging.
Sorry, somebody answered in the chat.
Oh, it's already answered in the chat. Okay. Yeah, so it is factor. Yeah, so it is variance standardization method, but I kind of want to go over kind of the details of how it's doing that. Okay, so number 1, lavaan uses default marker method. Okay, which means it fixes the first loading to 1. That means we have to override the default marker method, right? So to override that, you free the first loading, right? So you override that. Now you have, but then to do variance standardization method, you have to fix the variance to 1, right? So that's what this is doing. And like someone said before, Double tilde means covariance, but a covariance of something with itself is the variance. So this is the variance of the factor. Any questions about why we do the NA and the 1 star? So there is like an easier way to do that. I don't know if I covered that. Okay. It is on the web page though. So if you want, you can look at the web page, but basically instead of doing this manual way, you in the CFA syntax, you can add std.lv equals true. And that's another way to do exactly what we just did without standardizing. You can leave it as default marker method and then do standard LV equals true. You can see that in the website. So that's more incentive for you to read the website. There's way more material on the website. Okay, so let's look at the output. Let's look at the estimate column. How do I know that this is now the variance standardization method? I think you guys know based on what we've talked about.
Because there's no blank row for any of the variables.
Right, the loadings are all filled out. There's no, yeah, okay. So that's one hint. Anything else?
And the F estimate is 1.
Yeah, and more specifically, we're estimating the variance here, right? So these are the loadings and then these are the variances. So really good job. And that's exactly how we know that we've done the variance standardization method when we fix the estimate to 1, all right, for the variance. Now, if we didn't do the NA star, we would have seen a 1 here. Is that okay? Well, technically it'll still run. I guarantee you it'll still run, but you're kind of like restricting, you're fixing too many things, right? You want to just identify model, but then you're artificially saying that that loading is now 1, which you don't want. Okay, so really good job. And then, so how do we interpret, like, let's say item the Q04 then? So basically now this is the factor is now 1. So the factor variance is now standardized. So you can think of it as like a standard deviation increase, right? So for 1 standard deviation increase in XPSS anxiety, so this is SPSS anxiety. Remember, it's a latent variable, so it's a circle. So for 1 unit increase in SPSS anxiety, item 4 goes down by 0.665 points. Now, be careful because the item itself isn't scaled to 1, the variance, okay? So it's in the original metric of item 4, okay? But the variance of that factor is now scaled to 1. So for 1 standard deviation increase in SPSS anxiety, I dream that Pearson is attacking me with correlation coefficients, goes down by 0.665 points on the Likert scale. Any questions about that? Okay, and then finally, this is something I haven't talked about, but there's another way of standardization. So we've talked about marker method, we've talked about variance standardization method, and then there's something called the standardization method. So first of all, the syntax. So the summary, right? We can basically do the same model, but all we have to do is say standardize equals true. And honestly, this is the shortcut way to do everything all at once, okay? So you don't need to do any of that NA, whatever stuff that I just showed you, if you just put in standardize equals true. How do I know it gives me all 3 things? Well, you guys know that, okay, let me show you, okay, column 1, column 2, and column 3. You can put it in the chat too. Which one is variance standardization method? Column 1, 2, or 3? Okay, got 2. Good. Which one is marker method? Yeah, exactly. One is marker method. You know that because this fixes the one, right? The loading to one. So good job. This is mark. Now, the only thing we haven't seen is 3. Okay. So what is 3? 3 means, if you guys have looked at standardized beta coefficients in linear regression, that's basically what this is doing. What it's doing is not only is it standardizing the variance of the factor to 1, STD all, but it's also standardizing the items themselves, kind of like dividing by the standard deviation of the item too. Okay, so it's kind of like a correlation coefficient then. It's standardizing both the beta coefficient. A standardized beta coefficient of linear regression is standardizing by both the predictor and the outcome, which means the factor and the item. So for one standard deviation increase in SPS anxiety, item 4 goes down by 0.701 standard deviation units. So that's the difference, the standard deviation units. So essentially, this is like a correlation, right? And this is what you see more typically when you talked about standardized loadings. Okay, so when you see standardized loadings, typically it means this one, not the standard LV. The reason why we like this standardized loading is then you can kind of compare these relative to each other. So for example, the loading of item 3 is the magnitude of it is lower than the loading of item 4, right? 0.54 is lower than 0.701, but it's just flipped. The sign is flipped. We can also look at it relative to 1 or -1. So which one has the highest loading? Then we can say that item 4 has the highest loading, the magnitude. The sign tells us the relationships between the items. So so basically, item 3 has a positive relationship with SPSS anxiety, and item 4 and 5 have a negative relationship with SPSS anxiety. And you have to kind of basically check if you have some like reverse coding going on, because ideally you don't want the signs to flip. The other way you can check that the variance of this factor is scaled to 1 is looking at this, okay? The variance is 1. Notice though that the residuals are not different, right? Between the STD LV, even though they're both 1, the residuals are different because this actually standardizes by the items themselves, whereas this one leaves the items in the original scale. Any questions about interpretation of these columns? Okay, so I know that's a lot of information. So what we're gonna do is we're gonna take a break, okay? And we'll come back at maybe 2:30, all right? So feel free to ask questions to me before then.
Could I ask a quick question?
Yes.
About adding the intercept, when would you want to do that?
Okay, so generally it's good to have the intercepts estimated if you have full data. So if you don't just have the correlation table or the covariance table, and you have the full data, it's usually good to estimate the intercept. I just didn't want to show you the intercept because it actually adds more like parameters in your output. But it's definitely something you can estimate, and it's just the interpretation is not that interesting either. And so, because most people care about the loadings, and I think that if you, for CFA, if you just look at the loadings, that's really what's important. Some people don't really care about the intercepts, and that's why it's not really part of the output, but you can certainly estimate it. And I encourage you to do it if you have the full data available.
Okay, but it wouldn't change the loadings, right?
No.
Okay.
Yeah, you can try that, but I don't think it will change the loading. Yeah.
So does adding intersects to the model, does it make the model just identical? Or it doesn't have any?
Can you say that? You're cutting in and out. I can't really hear you.
Adding intercept to the model, does it make the model just identified?
That's a good question. Okay, so the model parameters are independent from the means and the covariances, right? So the known values will add additional parameters based on the mean you're estimating. So you're going to subtract those out anyway. So it's going to be just identified even with the intercepts. Okay, so that's a good question. But it's basically going to be like p times p plus 1 divided by 2 plus p. And then by estimating the intercept, you're going to cancel out the p anyway. So your degree of freedom is going to be the same. Any other questions? I know. So this is the thing, and the exercises will help, Kim, is this is assuming, I was looking at that too, and I was like, the relationships look kind of weird with these 3 items. But this is basically because we're not using the full survey, okay? So by using only 3 items, is it really assessing SPSS anxiety, or is it assessing something else? The more items you have, though, the more sure that you're going to, and when you run the exercises, you'll see that the patterns actually kind of change. And so this is my argument, is that the more items you have, the better, more reliably you're going to estimate the factor, okay? Here, we're only taking a small subset of the SAQ. The SAQ actually has 20 items, and I'm only even taking 8 of those, right? So definitely, yeah, look at the exercise a little later and see the loadings there, see if they change a little bit. But yeah, okay, so yeah, so basically, having those 3 items doesn't necessarily reflect SPSS anxiety, and you're going to see some kind of a strange kind of relationship there. The other thing I want to tell you is that this data set is completely made up, okay? So I think literally, if you guys have heard of Andy Field, I kind of like borrowed the data set from him, but basically I think he literally just like used the computer and like randomly generated some numbers. Okay, so don't over-interpret anything here, because the direction and the things may be messed up only because it's a fake data set. Okay, that's the real reason why you're seeing strange patterns.
Johnny,
Yeah.
there's been
Yes.
a couple questions about when you should use the marker method versus factor the variance standardization method.
Oh, okay. Honestly, in my experience, you don't use any of them. You use the standardize all method. The market method and the variance standardization method is literally like, what's the default, and then like, what's a solution, what's an alternative solution. Now, those 2 are going to be standardized using the standardize all anyway. Okay, so regardless of marker method or variance standardization method, that's just to identify the CFA. But then in terms of interpreting, usually you just use STD all. Now, there's a special circumstance when you don't want to use STD all, and that's when you have categorical predictors. We're not going to go over that, but basically, if your predictor is like a categorical variable and it's like 0, 1, let's say dummy variable, you don't want to standardize by the item, right? You want to leave that unstandardized. Okay, so that's kind of the only situation when you use standardized LV. But just think about it in terms of like, okay, these are kind of ways to identify the model, and then the interpretation really comes from the standardize all. Oh, it's 2:30. Okay. Did you guys get enough break? Maybe it's not enough break. All right, so we just have 2 more topics. Really, like, this is the harder one. So like, if you have enough brain power to pay attention, I appreciate that. But it's going to go quicker because I kind of removed some of the very, very technical stuff based on my colleagues' suggestions. So The last thing we're gonna, well, the last two things we're gonna talk about, and this is really the major thing, is model fit, because we talked about degrees of freedom, right? And then we wanna make sure that the degree of freedom is positive, so we have an over-identified model, right? And this is where we talk about, okay, so how, now that we have an over-identified model, how well does this model fit? Now, basically, did we have a over-identified model with our 3-item CFA? No, right? Because that was just identified. So can we even talk about model fit with these? No. So that's why for model fit, you really want to consider models that have more than 3 items, because a 3-item CFA is just identified. You want to have more than that. So this is the situation when you have more than 3 items, and we'll do that in the exercises. So the first thing you want to know is the model chi-squared, and the second thing you want to know is approximate fit indices. Okay, so this is where it gets a little math stat kind of. Okay, so if this is not like ringing true, and I know it's like kind of a lot to process, don't worry about it too much other than how to like interpret the p-value, okay? All right, so the hypothesis in a CFA, and this applies to SCM too, if you're interested in SCM, the null hypothesis is that we already know these terms though. The model implied covariance matrix equals the population covariance matrix, right? If you think about conceptually what that means, that's just basically saying that my model reproduces the population. That's basically what it's saying is my model good enough to perfectly reproduce the population? And note that this is an example of exact fit. Okay, it just means it's exactly equal, which may or may not be true. But this is why this is called an exact fit hypothesis. And we'll talk about close fit later. But basically, you want this to happen. This is called an accept support test. This is counterintuitive because in a linear regression model, you typically want a reject support test. So you want to reject the null hypothesis because you want this to be not true. But in a like in a linear regression, you want the beta coefficients to be not 0. But in an SCM or CFA, you actually don't want this, because what is this saying? This is saying that the model implied covariance matrix is not equal to the population. So that's actually a bad thing to do. So what we do want is to accept, quote unquote, or fail to reject the null hypothesis. And what does that mean for our p-value? Do we want our p-value to be less than 0.05, or do we want our p-value to be greater than 0.05, assuming our alpha is 0.05? Yeah, Kim said greater. That's exactly right, because by having a p-value greater than 0.05, we are failing to reject the null hypothesis, which is an accept support test. Very good. So we want this, right? Now, just an aside, it's actually kind of important. Given that we want to accept the null hypothesis, sample size is actually a deterrent, right? Because the larger your sample size, so sample size or n is positively correlated with power, or the ability to reject the null hypothesis, right? So that's a catch-22 or a conundrum, right? Because by increasing your sample size, you gain more power, but you're more likely to reject your null hypothesis. Does that make sense? So that's kind of why we developed other things besides the chi-square, because this is basically measured by the chi-square. Okay. All right. So now, in terms of that's an aside. If you know from linear regression, we are estimating the population with the sample. Okay. So you know that the null hypothesis is regarding the population, not for the sample. This is the population on the left. This is the no. This is the population here, and this is the sample on the second row. Okay. This is the model. This is the covariance. So remember, we have the model implied covariance matrix. We have the population covariance matrix. Now we have the estimated or sample model covariance matrix and the sample covariance. We've seen all these terms, right? The only term we haven't seen is this one. What this is basically saying is that I'm going to estimate all the terms I see up above. When the hat means I estimate. So lambda hat, psi hat, lambda, transpose hat, plus theta epsilon hat. What we've seen before were all hats, right? So like all of these were hats, okay? These were all hats because these were all estimated from our sample. Does that make sense? Those loadings are hats. Those residual covariances are hats. What is the point of that? Well, this allows us to create what we call residual covariance matrix. And don't confuse that with this residual covariance matrix, okay? What this is saying is this is the sample covariance matrix minus the model implied estimated covariance matrix. Why is that interesting? Because we're trying to say something about the population. What we have is the sample. Now in the population, what is the corresponding mapping is sigma minus sigma theta. In the population, what is the difference of sigma minus sigma theta? Look at the null hypothesis. Under the null hypothesis. Yeah, it's 0. Good job. Oops, sorry. But that's a great response. But in our sample, is this necessarily equal to 0? Well, I argue that that's not necessarily equal to 0 because the S may be off in terms of estimating the population covariance, and the model might be off in terms of estimating the model implied variance. So there's sampling error. Well, you should be getting then, if it's truly 0, you should be getting things like 0.01, you know, maybe negative 0.05, you know, values that are close to 0. If you get 5 million, that's not good, right? So you want this to approach 0. And that's really kind of what the goal of this is you want to make sure that your model in your sample reproduces the sample covariance matrix as much as possible. So here's where we get the second poll to see if that makes sense to you. Okay, if you have some time, I'm going to launch the poll now. I'll read through the questions, there's 3 of them. The residual covariance matrix is defined as the population covariance matrix minus the model implied covariance matrix. It will never approach 0, but can approximate 0. Second, the goal of SCM, or I actually mean CFA, it's the same thing. It's to recreate the population covariance matrix using model parameters. Therefore, we do not want to we do want to reject the null hypothesis. And then finally, the larger the sample size, the more likely we will reject the null hypothesis. I'm talking about CFA too. SCM and a CFA are basically the same thing. Okay, so let me get something first while you do that. Okay, I'll give you guys maybe like 30 more seconds. I would say the number 1 is probably the trickiest. And don't worry if you get it wrong. Like, sometimes I'm just trying to trick you on purpose. And my intention isn't to make you feel bad. It's really just to get you thinking about like, okay, what exactly am I saying here? And once you get it wrong, then you'll know exactly why you got it wrong, okay? That's part of the learning experience. Okay, I'll close it in about 10 seconds. 5, 4, 3, 2, and 1. Okay, so the first one was kind of hard, I guess. So the residual covariance matrix is defined as the sample covariance matrix minus the sample model implied covariance matrix. So remember in this, you can move the window if it's bothering you. Okay, so what I'm talking about is this thing here, right here. I'm not talking about this thing on the top, right? So what I was asking in the thing is this equal to the sample residual covariance matrix? No, because this is exactly 0 in the population, remember? But this should approximate or be close to 0, which is the sample. Okay, so the residual covariance matrix is talking about the sample because in the population, this in the under the null hypothesis, this will always be 0, remember? So that's why number 1 is false. Number 2 is false because this is an accept support test, not a reject support test. So we actually, and you guys got this one, we actually want to not reject the null hypothesis. And 3, the larger the sample size, the more likely we will reject the null hypothesis. And that is exactly why we have approximate fit indices. Any questions about the quiz before we go on? Okay, so this is basically what we're talking about in terms of the model chi-square. This is the model we just fit. This is a model that you're going to do in the exercise with 8 items. Remember, the model we just fit is just identified. And how do we know that? Because the degree of freedom is 0. Now you know exactly what this means. That also means the test statistic is 0 because you can't calculate it. You know what these are, right? Free parameters. Now, let's say we have an 8-item factor analysis, 1 factor. Then we have 16 free parameters. And now we actually have a degree of freedom that's positive. That means it's an over-identified model. And then we can actually assess the test statistic. Now look at the p-value. What is this saying about our null hypothesis?
The null is rejected.
The null is rejected, right? So that's actually bad, right? Because if we wanted this to be a model we want, we actually just said, nope, this is not the model we want. We rejected it. That's a problem because our sample size, remember, was 2571. And the fact that it's such a large sample size means that we're probably going to get a p-value less than 0.05, which means we probably are going to reject our model. So that's the conundrum, right, that I was talking about. Okay, so this is where these kind of approximate fit indices come in. So what we talked about was exact fit. Exact fit means, sigma theta equals sigma in the population. Approximate fit kind of doesn't force that to be true as long as you're kind of close, okay? So there's 2 types of approximate fit indices. Oh, is there a question? All right. So there's 2 types of fit indices, okay? There's absolute and incremental. You don't have to actually know what that means. But basically, there's CFI, TLI, and then there's Rmsea. Those are the main ones you want to know, okay? All right, but before we do that, we have to know what a baseline model is. Okay, so remember the variance covariance matrix, okay? But this is sigma theta, okay? So what this is saying, the baseline model is basically, if you look at the path diagram, what are these basically estimating? Well, we see these are estimating residual variances, but there's nothing predicting it, right? So if there's nothing predicting there's no like factor predicting it. So what do you guys think then the residual variance is? If there's nothing predicting it. There's no residual, right? So the residual variance is literally the variance. Okay. And what are we doing with these? We're basically estimating variance of y1, variance of y2, all the way down to variance of y8. Do you see covariances in this diagram? No covariances, right? What that means is then in our model implied covariance matrix, if you look at the highlight, we are estimating the variance of y1, y2, y3, y8. But we are not estimating any of the covariances. This is called the baseline model. Why is that called a baseline model? It's the worst model because in reality, variables are probably related to each other. And that's why we're doing the factor analysis, right? Now, what do you guys think the orange one is? What is this saying? Just think about what the opposite model of a baseline model. Yeah, right. So not only are we estimating the variances, we are estimating all possible covariances. And this is an upper triangular, so it's the same. In that case, the known values equals the number of parameters, and our degree of freedom is 0, right? Doesn't this look familiar? What kind of model is this? Saturated, yeah, exactly. And the other term for that is the just identified, which is exactly what we've been doing, right? Just identified or saturated. Okay, really good job. You guys are still awake, good job. Okay. To understand fit indices, you have to understand the difference between a baseline model and a saturated model. And think about where your model lies. Your model is somewhere between a baseline model and a saturated model. And that is the premise of fit indices. Okay, so bear with me here. This is as simplified as can make it without going too technical. What these approximate fit indices are saying, especially for CFI and TLI, not necessarily for Rmsea. Think about the denominator here. Let's look at the denominator. Remember, the baseline is the worst model. The best model is the saturated model. You can take the difference, right, of the saturated model to the baseline. That's the biggest difference you can see, right? That's the denominator. What about the numerator? Well, your model, called the user model, is somewhere between the baseline and the saturated, but how much between is it? So what you do is then you take the difference of these, divided by the difference of the best to the worst. What would this ratio be if your user model was the saturated model? One, good job. Perfect. You guys are getting it. That is why we want, for example, the CFI and TLI to approach 1. Now, if you think about the opposite, if your user model is now shifted towards the baseline model, you're going to approach 0, right? 0 over 1 is 0, so that's bad. That is why you want the CFI and TFI to be between 0 and 1, TLI, but approach, or sorry, it should be in between, right? But approaching 1. Okay, so that's kind of the rationale for why you want a CFI or TLI to be close to 1. The Rmsea is just a little different, okay? Basically, remember we talked about exact fit? That's exact fit for the model chi-squared. The Rmsea just does something a little bit different where we talk about close fit. And basically, you don't have to know too much about like the null hypothesis, but this is what we call a non-central chi-square. It doesn't matter. Basically, what you have to know is if you get an Rmsea of less than 0.05, it satisfies close fit. If it's between 0.05 and 0.0 fit, it fails close fit, but it doesn't fail poor fit. So it's kind of in between. Okay. And then anything greater than or equal to 0.10 is poor fit. So that's not good. Okay. So if you have something like close fit or approximate close fit, then you're good to go for Rmsea. Okay, so this is just kind of a summary. The model chi-square, remember, it's likely to be rejected given the large sample size. Okay, reject more often, more likely. The CFI, remember, ranges between 0 and 1. Well, how big approaching 1? They say between 0.9 and 0.95 is good. Okay, so usually you want the CFI to be 0.95. TLI can be a little lower. It can be around 0.9. The CFI is always going to be bigger than a TLI. And then the Rmsea, you want it to be less than or equal to 0.05 for close fit. But honestly, I see a lot of people have, approximately close fit. Okay, so between 0.05 and 0.08 is okay. Okay, so let's look at the because we couldn't do the fit for the 3 item. I just show you a fit for the 8 item, and you'll be doing this in the exercises actually. But this is just a quick overview of what you're going to look at. So in terms of the lavaan syntax, you're going to add this right here. Fit that measures equals true. Remember the standardized true is just to get the standardized loadings. This is the only thing you add in the summary, okay? You'll be fitting this a little later. Now, we note the number of observations is 2571. That's big, right? So we're probably going to reject our null hypothesis. Well, that's the model chi-square with 20 degrees of freedom. This is the baseline, remember? It's the model where we specify only the variances and not the covariances. We have higher degrees of freedom because we're freeing up 8 additional terms. Don't worry about the p-value there, but that is the baseline model. This is what you're going to use to calculate the CFI in the exercises. Now, the important part, let's look at the CFI. What do you guys think? Well, the criteria was 0.95, honestly. We don't even satisfy 0.90. Okay, so it's not great, okay, but it's not terrible. Let's look at the Rmsea. Okay, it says poor fit, basically. Now, looking at the confidence interval, that's actually kind of useful, is you kind of want to see if this confidence interval, the lower and the upper, kind of reach the close fit and the lower, and then the poor fit in the upper, okay? So if your confidence interval was something more like this, then I'd be happier, right? Because then you satisfy close fit in the lower, and then you satisfy approximate fit in the upper. Approximate close fit. But here, let's look at the lower. The lower is barely, it doesn't even satisfy 0.08, which is kind of our requirement there. And then the upper goes pretty much equal to 0.10. You see that? So that's not really good. And the p-value is you reject the close fit hypothesis. So that's not good. Finally, you have this root mean squared residual that comes from the S minus sigma hat. We haven't covered that, but basically that's where it comes from. And then you just kind of standardize that and you take the square root. You want this, close to 0, right? So this is actually okay for the standardized root mean residual. So my point here is that you need to take into context all the fit measures that you're given. Now, from an overall picture, though, it looks like this isn't the best fitting model. Okay. So can you guys think of ways to improve the fit of a model in CFA?
Can we add more factors?
That is good. Okay, so yeah, so like for example, if like, there's actually 2 factors that load into, like 3 items load into 2 factors instead of 1 factor. That's a good suggestion. Okay, what's another suggestion? Because you're going to face this problem, I guarantee you, when you run your analysis. You're like, oh no, my fit is terrible. What am I going to do?
Can you look at the fit of the individual items and then potentially remove some?
That is really good. Yeah. So if you look at the loadings of some of them, let's say some of them, and I'm talking about standardize all, but let's say some of them were 0.8, some of them were 0.2. Well, maybe you want to remove the one that's 0.2 and then reassess the fit of your model. Okay. So those are all excellent suggestions. And, like, honestly, CFA is kind of iterative. You kind of have to play around with it. Just know that the more things you do with it, the more you capitalize on chance, okay? So I won't talk about this in this beginner seminar, but there's something called cross-validation that I recommend. And that's basically splitting your data set into a testing and a training data set, or training and a testing. So you start with the training and then you test it, okay? So let's say you have like 2,500. Let's say the first 1,571 we train, and then the next 1,000 we test. Okay, so you can like fit as many models as you want in the training, like remove items, add more factors, and then you settle on one final CFA, and then you do the test and then see if this fit is good there. If your fit is good, just as good as in the training, then you've cross-validated your CFA. Does that make sense? And if not, request the advanced seminar for CFA. All right, so those are great suggestions in terms of improving the model fit. Okay. Okay, we're not going to take a quick, because this is really quick. Okay. So basically, like someone suggested, sorry, I should know your names by now, but I haven't looked at your name. But I think you've been responding a lot. But basically, we can think about adding 2 factors, right, instead of 1 factor. Well, just know that lavaan does something by default, okay? Not only does it do marker method by default, it also does the covariance by default, okay? So by default, lavaan will covary the factors. And if that's not what you want, you have to turn it off. The other thing is this. Notice how many items are loaded onto factor 2. Let's say this is like now SPSS anxiety, but then this is more like computer anxiety, like overall anxiety with technology. Okay, so that's kind of what I mean by like a second factor. SPSS anxiety and computer anxiety should be correlated, right? But what if I only have 2 items, like computer, I hate using computers for Y6. I don't even remember, but let's say this is like, I don't know how to fix a computer or whatever, right? Let's say you only have 2 computer items in your survey. But what did we remember about identification? Remember that for identification, we needed 3. Okay, so I won't go over the details. This is basically going to be in my advanced seminar if you take it and if you want it. by correlating the factors, it automatically identifies a 2-item factor. Okay, so you have to have a correlation with another factor to identify a 2-item factor. Okay, but otherwise, this is under-identified. If you didn't have any of this, this would be under-identified. Okay, we won't cover that here today. All right, so what standardization method are we using here? Are we using marker or variance standardization? Variance standardization, right? Can we use marker? Of course. Can you mix and match? You can. Like you can do, I think you can do one here and then do variance one here, but I wouldn't recommend it. I just basically choose one. Okay. Now in terms of lavaan, basically you just do a second factor, right? So instead of calling it F, we're going to call it F1 and then F2. And then there's 2 items that load onto F2. And then there's 1, 2, 3, 4, 5 items that load onto F1. Now, maybe this is a trick question, but like what that method am I using here, standardization?
Variance standardization.
Yes. How do we know that? Because we have this right here. But it's a trick question because by default, lavaan specifies marker method, okay? So it's actually overriding the marker method by specifying std.lv equals true. So good job. And finally, when we say standardized equals true, we get all 3, okay? So it's actually a trick question. Okay, so, but basically, you know, you can look at the, yeah, we know that this isn't marker method, right? Because the variance isn't, and the loading isn't 1. I just like looking at this, honestly. This is the only column that I really look at when I look at CFA right here. And then you will notice that, you know, these loadings, what do you guys think? Well, the loading should be between, the standardized loading should be between 1 and -1, right? Where 1 is really high and -1 is really high in the opposite direction. These don't look that high to me. Okay, why is this not high? Well, if you look at the variance explained by that factor, you square it. Okay, I didn't talk about that in the seminar, but I do talk about it in the EFA one. So 0.19619 squared is 0.38. That means 38% of the variance in statistics makes me cry is explained by SPSS anxiety. Let's look at this one. 0.498 squared is only 0.25-ish. Only 25% of the variance in Q8, you guys tell me what that is explained by SPSS anxiety. To me, that's bad, okay? So if you have a loading that's like 0.4 or 0.5, that's actually not that good. And this is kind of the reason why we're kind of getting low CFI too, okay? So the loadings kind of determine your CFI. Okay, so this is not the best fit. Honestly, none of these are really great factor analysis models. I'm just showing you the real world because, you know, in textbooks, they always show you like perfect data. Like this is the real world where you're not going to get perfect data, okay? And some of the correlations, the direction doesn't make sense sometimes, okay? So that's reality, okay? So that's kind of the loadings. Now the new term we have here is this, right? And remember the double tilde means covariance. This is the covariance. And actually you can think of it as a correlation because they're standardized now here. This is the correlation of factor 1 and factor 2. That is pretty high to me. That means that SPSS anxiety and fear of technology is highly related, but they're not perfectly related, so you're not going to get a 1. Okay. And again, these are the residual variances. And then these are the variances of the factor. And we know that these are standardized because these are 1s, which means this is not marker method. This is variance standardization method. And this is not variance standardization method. This is standardize all because I see the residual variances are different from the variance standardization method. Any questions about that? I think that's kind of the major thing that I want to talk about. And then finally, what if you want to uncorrelate? What would you do to uncorrelate these factors?
Set the covariance to 0.
Exactly. Good job. Okay, so basically right here is the extra term. F1 covary with F2, set the covariance to 0. Perfect. Now, you probably don't expect this, but this is the output you get. Okay. Anyone have an idea of why this is giving me this warning? Now you're the tech support.
CFA by logic वही है ना कि एक ही step.
Can you say that again, or if you were talking to me? So why is this giving me an error? I ran it's not the syntax. I guarantee you it's not the syntax. This is where you have to kind of know about identification.
Because now F2 will not be identified. We have only 2 items.
Yes, perfect. Okay, so like I said before, and perfect job of understanding that is that we have a 2-item factor here. And when I said it's identified, it's when these are correlated, but now I turn these off, whoops, and those are no longer identified. Very good job. Okay, last poll, and then we get to the exercises, okay? Thanks for bearing with me here. Okay, so number 1, by default, lavaan correlates the factors in a 2-factor CFA. These are pretty easy. 2, either marker or variance standardization methods can be used for 2-factor CFA. And then 3, turning off the factor covariance that's probably the trickiest one. Turning off the factor covariance is an assumption. It doesn't mean that there's actually no factor covariance in my system. Yeah, I made this one a little easier because I know the other ones were like super challenging in terms of like trying to trick you. This one should be pretty straightforward. So trust your instinct. I'll give you guys maybe 20 more seconds. All right, 5, 4, 3, 2, and 1. By default, lavaan correlates the factors in a 2-factor CFA. That's true, right? So if you just like leave lavaan, it's going to do marker method, covary the factors. Does that mean I can use variance standardization method? Of course, right? You can use any of them. You just have to say which one you do in this in the summary. And honestly, you could just get all 3 with standardize equals true. Okay, the third one is you guys got it right. But I just want to be clear because a lot of people are like, okay, so if I remove the covariance, does that mean my factors aren't correlated anymore? Yes, but that's an assumption, right? Just because you say it's 0 doesn't mean it's actually 0. The data is the data, right? You're still going to have a covariance structure, but what does that imply about your model fit if you have a covariance between factors and you constrain it to 0? It's an incorrect assumption, right? So your model implied covariance matrix isn't going to match the population. You're going to get a low fit. Good job. Okay, so this is the intermission. Yeah, go ahead. Yes, go ahead.
Under what circumstances should you set the factors covariance to 0?
Almost never, because you can always covary first and then see if the correlation is near 0 and then fix it later. But remember, you have to do cross-validation, okay? So just remember, you have to do cross-validation if you want to do that, okay? All right, so this concludes the lecture portion of the seminar. What we're gonna do is we're gonna take a quick break while you set up your R Studio. And then we're gonna go over 3 exercises if we have time. Otherwise, we're going over 2, okay? So this is where we kind of get more interactive, and then you can like kind of play around with lavaan. All right, so let's resume at 3:15, okay? I'll give you some time to kind of set up lavaan or R. Okay.
I had a real quick question.
Yes.
So with the data that we're dealing with right now, and I'm guessing with a lot of the CFAs and SEMs, you're going to be dealing with Likert scale type data.
Mhm.
And you were saying earlier, I just wanted to make sure I understood you clearly. You don't really have to specify that the data is ordinal in that instance, as long as it's normally distributed.
Yeah, that's a great question. Honestly, ordinal regression models were developed much later than factor analysis. So like if you know like ordinal logistic regression, that's something that wasn't developed until much later when they developed something called generalized linear models. And that was like, I don't know, like 80s or something. So factor analysis was developed in like 1900s. Okay, so you're not going to get a lot of overlap there. And really, as long as your data is like, let's say the number of categories is like around 4 to 7, I think that's okay. As long as it's not like 2, right? It's not like a binary yes, no. There's
Right.
other methods to deal with that. But yeah, you wouldn't treat it as ordinal. You would treat it as continuous.
Okay.
And-
And then this failed normality, I think there's like some other
Yes,
estimation methods you could use to handle
exactly.
that.
There's
Okay.
things called the chi-squared correction, something called Sator-Bentler. Bentler was my advisor. So Sator-Bentler adjusts for the chi-squared to make it so that it works with non-normal data or skewed data. There's also other estimation methods like weighted least squares. So those are kind of like solutions they come up with if you have like non-normal data or categorical data. And then M plus is definitely the way to go if you want to work with categorical data. There is something called binary factor analysis or categorical factor analysis. And to my knowledge, lavaan doesn't do that. So
Okay.
yeah, so that's really a limitation of the software and the technology, because those techniques were developed much later. Like these methods were probably developed in the 80s versus like the 1900s. Okay, so lavaan is not like it apparently is still beta software, so it's not actually that well developed compared to M plus, for example.
Okay, great. Yeah, I'll have to I've tried Lizral before.
Wow, you've tried Lizral. That is the heart of SCM. And if you understand Lizral, you will understand every other program. So that's great that you understand Lizral, because that's kind of how I taught my SCM class or seminar. But yeah, if you understand Lizral, you will understand M plus for sure.
Great. Thank you very much.
Okay, so thank you all for staying till the end. This is the part where you get to, you know, get your hands wet a little bit, because we're gonna do some exercises, and basically you're gonna work with lavaan yourself, okay? So exercise 1 is kind of what I was doing before when I showed the model fit index. Remember, 3 items CFA, you're not going to get any model fit indices. So I want you to practice getting some out of lavaan by fitting a CFA with all 8 items in the SAQ. So that's just Q01 to Q08, and then fit with all 3 methods. Okay, you can either do it manually if you want more practice. I encourage you to try it manually and then do it with the shortcut method that I showed you. Kind of interpret the loadings and then assess the fit. And then name some reasons for the poor fit, okay? So what I'm gonna do is give you maybe 5 minutes to do that. So 3:23, let's say. Yeah, lavaan does not do EFA. So I'll give you until 3:23. You don't have to finish it. You just have to, you know, start it. So you kind of get an idea, okay? And I'm not going to tell you where the answers are, but it's there somewhere. So I would encourage you not to look at the answers when you're doing this yourself, and just try it, okay? The real way to learn is to just do it yourself. The beauty of lavaan is that the syntax is so easy that I'm sure you can pick it up. And then this is where I encourage you to be like interactive, like if you have a question, or just unmute, or like if you want to share like how you're coding it or something, and then how you interpret it.
Are we doing 1 factor for this one?
Yes, 1 factor. And I'm gonna show you like kind of my code and see if you can catch like the error. Because you know, sometimes you code it, you're like, wait, why is there an error? And then you realize you like flipped the sign, or you left out a quotation mark or something, you know? So Nandini, so I'm gonna leave some time after the exercises to answer any other questions, okay? So hold off on that, and then we can address them after the seminar, okay? All right, so how do you guys feel about doing it? It's not too bad, right? I think it's just getting the syntax right. The good thing is we already kind of did this during the lecture, right? It's just really like for you to kind of practice. Okay, I'm gonna share, and then you tell me what I did wrong, okay? Because I literally made this mistake. Okay, so this is my model. I specified the factor, right, using these 8 items. And then I pass the model 1 into the CFA function. And then I request fit.measures equals true and standardize equals true. Okay, so do you guys see anything wrong with this? So what was the error? Yeah, violet. Okay, so I think I just flipped the equals with the tilde. Let's see if that works. There we go. Okay, so yeah, the syntax ordering really matters, okay? And this is a 1 factor CFA, like we were saying. Anyone want to volunteer in terms of how to interpret either like the marker method or the variance standardization? That's kind of hard. Like pick an item, let's say. No, it's kind of scary, right? Okay, I'll interpret the marker method. So like this is saying, let's look at item 4. So this is saying for a 1 unit increase, right, in SPSS anxiety, then the item 4 increases by 1.3 units on the scale of item 1. Okay. How about this one? Okay, no volunteers. All right, so this is basically for one, let's see, one unit increase, no, 1 standard deviation increase in SPSX anxiety leads to a 0.55 increase in item 5 in the original metric of item 5. Okay. And finally, what about the last column here?
For 1 standard deviation increase in our factor, item 5 goes up by 0.574.
Perfect.
Standard deviation units.
Perfect. Thank you. What is your name?
Dano.
Daniel?
Dano.
Where are you on here? How do you spell that?
It's D-A-N-I-L-O.
D-A-N-I-L. Danilo?
It's Danilo technically.
Danilo. All right. Good job, Danilo. Okay, so yeah, so like Danilo said, it's basically these are kind of like standardized units in the Y and the X, right? In the predictor and the outcome. So you can kind of see these as correlations. Now, basically, then what I look at is, okay, what are my loadings like near 0.8? No. And what's my worst loading? Item 2. That's really what I look at. Okay. And you know, some programs they even cut off certain like for EFA, they cut off the loadings at 0.4. So if it's less than 0.4, they cut it off. Okay. So that let's look at the fit. Well, we already saw the fit, right? The CFI was 0.87, TLI is 0.81. You know, the criteria should be 0.95 and 0.9. And then the Rmsea, it fails the test of close and approximately close fit. So honestly, this isn't the best model. And like we said, to improve the fit, you know, what's one way? Well, we can maybe remove item 2. But honestly, like it just doesn't look like there's a strong correlation between a lot of them, like Q8. We can kind of reconsider our hypothesis, and like someone said, is to consider a 2-factor model, and then maybe some load more onto each of those factors. And if you try a million things and then you still don't see it panning out for you, it means you need to reconsider your hypothesis. Okay, if your hypothesis is that this is measuring SPSS anxiety and you're getting super low loadings, it means that these measures are not reliably measuring the same thing. So think about like changing your hypothesis. Maybe this isn't SPSS anxiety that you're measuring. Yeah, and I won't talk. Yeah, go ahead.
If I'm adapting a scale, then all I need to show is all the items are loading onto the factor, right?
That is the first step. Yes, you have to make sure that the loadings are high, that you get a high CFI, TLI, and a low Rmsea. That's the first step. And then I won't talk about the other stuff, but basically there's something called validity. So you have to make sure that your scale correlates with an established scale. Okay. So that's that. Yeah. So that's called validity. That's called construct validity. But I'm not going to talk about that here. Okay. All right. So how do you guys feel about that one? Not too bad? Maybe the interpretation was a little tricky, right? But honestly, like most people don't interpret the marker method or the variance standardization method. They really just interpret the last column, which is the standardize all method. Okay, so second exercise, we're going to now, like someone said, let's try to see if, let's fit the first 4 items to factor 1 and the second 4 items to factor 2. Choose any standardization method. You can do all 3 like we did. And then what I want you to do is remove the item with the lowest loading. How about remove the item with the lowest loading in each factor? That's what I meant, okay? So not all the items with the lowest, but the lowest loading in each factor. Now compare the fit of that to the first model you fit. And then finally, uncorrelate the factors, because by default it's correlated, right? And then compare the uncorrelated model to the correlated model. And what I mean by the uncorrelate the model in B. Does that make sense? And I'll give you 5 minutes to do that. You don't have to finish this. It might take more than 5 minutes. It might take less. But just get to as many as you can. Yeah, like absolute value, exactly. Kim.
For the uncorrelated 2-factor model, do you want us to fit, use all 8 items again?
No, use the one that you whittled down.
Okay.
Mm-hmm.
Johnny,
Mm-hmm.
would you be able to say a word or two about AIC, BIC?
Yeah, okay, so AIC and BIC are not that commonly used in SEM because there are so many other fit indices like the CFI and the TLI and the Rmsea. Those are pretty good for what you need to do in general. I only see the use of that when you're running a model that doesn't have the CLI or CFI available. This can occur when you have like more complex models that were developed much later. For example, like when you have like categorical factor analysis, there's some models that don't even output the CFI or TLI. I know this is especially true if you have like interactions, like moderated factor analysis. That definitely doesn't have TLI and CFI. So in those cases, you're pretty much left with the AIC and BIC, and that is only a relative fit index. So basically, you're comparing it to another model. I wouldn't recommend using that unless you absolutely have to. Like if you have the CFI TLI available, you just use that.
Thank you.
Mm-hmm. Okay, how do you guys feel about this one? Okay, so first of all, which items did you guys end up removing? Okay, I got, yeah, so 2 and 8. Did everyone get 2 and 8? Yeah, like, let's see. Let me share my screen. So this is my first one. 2 and 8, right? Good. Yeah, and which columns did you guys look at? Basically, I just look at the standardize all, right? It's hard to tell, right? You can't use marker method really to compare it. You can kind of use variance standardization method also. And then I removed 2 from factor 1. And then I removed 8 from factor 2. Okay. Now look at the fit first. Okay, so CFI TLI 0.88, 0.82. Now let's fit the one where we remove them. Did you guys get 0.917 for the CFI and then 0.844 for the TLI? So yeah, if you get that, then what is that telling you? That's basically saying that this is, okay, good. Good, Anna. Okay, so that means basically this is a better model, right? Why? Because we removed the one with the lower loadings, right? So like I said, CFA could be an iterative process where you kind of like try to, you know, free or remove some of the low loading items. But this is where it crosses this line of, is it CFA or is it EFA? Because it's supposed to be confirmatory, not exploratory, right? So this is why you need to do something called cross-validation, like I said, to really make sure you're not capitalizing on chance. There's also something called modification index, which I didn't talk about today, but that's another way to kind of look at, okay, if you don't really know, like you let this like algorithm tell you which parameters to add. But yeah, go ahead.
Hi, Johnny, I have a question. So the first time I did it, I forgot to remove 8. So after I remove 8, so CFI went up and TLI went down a little bit, like it's 0.01. But how could that happen?
Wait, so you said TLI went down?
Yeah, because I typed it wrong because the first time I forgot to remove 8. Let me do this again.
Like you left this?
Yeah, so before I remove 8, the TLI is 0.861. After I remove 8, it's 0.844.
Oh, interesting. After you, so okay, so can you repeat what you did again? Did you do this?
Yeah, I did this.
Okay, let's see. You got this?
Yeah.
Oh, That's interesting, right? That's, you know, the strange thing is that the CFI went down, but the TLI went up, right? Is that what you're saying?
Yep.
That is interesting. It might have something to do with the formula itself, because the TLI uses something called relative chi-square, and the CFI uses basically the non-central chi-square. So there could be some slight differences in the pattern. But I think in general, that's why they developed those criteria. So you kind of just want to see if they approach 0.9. And the other thing is, if you're getting different results, you want to also confirm it with other things. Like, how about the Rmsea? Okay, did the Rmsea go down? How about the chi-square? Did the chi-square go down? Okay, so you want to confirm it with the other things too. Okay.
Okay, thanks.
So, yeah. All right, so I got that, and then you guys know how to unconstrain the covariances, right? By setting the 0 star. Now, what did you notice about the fit? Bad, right? Yeah, okay, so 0.65, 0.42, Rmsea 0.22, right? So just because you constrain your factors to be uncorrelated doesn't mean it's actually reproducing your data. That your data itself is uncorrelated. Okay, so you want to make sure that your model accurately reflects the data, and that's really the point of these fit indices. So good job. Okay, so do you guys have mental capacity to do another one, or do you want to just kind of end here and then ask questions? You can type it in the chat, or like, you want to do another exercise, or just end here and ask questions? The last exercise is hard. So just letting you know that if you'll get something out of the exercise, but oh, you want to do one more? Oh, good. Yay. Wow, you guys are amazing. You have really good attention span. Okay, yeah, okay, because I promise you'll learn something from it, okay? All right, let's go back to the exercise. Okay, this is the last exercise. I call it advanced. It's not advanced, but it just requires you to think a little bit more. And you really have to know what baseline model is. Although the secret is it's in the webpage. You just have to find it. And then the saturated model, you kind of have to think about that one. But let me read the exercise. So basically, what the point of this exercise is how to calculate the CFI yourself. And that way you'll kind of understand what the CFI is. But basically, remember, it's a comparison of the baseline model to the saturated model. So what you have to do is first fit the baseline model, and then fit the saturated model, and then use the chi-square and degree of freedom from those, and then manually compute the CFI. And I'll show you the CFI equation here. So this is the CFI equation. So first thing you need to do is get the chi-squared. You know how to get the model chi-squared, right? Chi-squared, test user, whatever. And then there's, yeah. But basically, you need two chi-squares. You need the baseline, and then you need the saturated. All right, so you need two chi-squares, you need 2 degrees of freedom, and then those are your delta, right? Actually, I don't think you need the saturated. So I'm just showing you so you can fit the saturated yourself. But basically, for to calculate this one, you need 2. You need the baseline and then your user one, okay? I was just showing you the saturated because it's useful to learn what a saturated model looks like, but you don't actually need that, okay? So let me rephrase that again. So first you need the baseline chi-squared and then the degree of freedom. Then you need your user chi-squared and your degree of freedom. And then you can take the difference of the chi-squared from the degree of freedom. That's your delta baseline minus your delta user. This is the user one over the delta baseline. You don't need the saturated, but I leave that as an exercise because like I wanted you to understand what the saturated model is for an 8-item factor analysis. So this is for all 8 items, remember? Okay, so if you want, I could leave this up, and then you can also find this equation in the webpage. And I give you a hint. Go ahead.
Sorry, can I ask a quick question about
Yes.
the fit measures?
Yes.
So if you're using CFI, SR, MR, and Rmsea, let's just say as your 3 fit measures, if you kind of pass 2 out of the 3 of them for cutoff, so you said like CFA has to be like 0.95, for example, if you have that, and then same with for SR, MR, if you kind of fit the cutoff for what's considered good, but you don't pass Rmsea, is that okay or considered acceptable if you're like past 2 out of 3 of those?
Yeah, so that's why there are so many developed, because you really want to take it in the context, right, of your whole model. So if you're saying 2 out of 3, well, okay, then you have to kind of look at your loadings. Make sure your loadings are high. Like you don't want loadings that are in 0.2 region or 0.4 region for the standardized loadings. If you see that, then you think about removing those. Additionally, if you're saying 2 out of 3 and then your loadings are all pretty high, then yeah, that's fine. So it really is in the context of other things too. Yeah.
Okay, perfect. Thank you. That's super helpful.
Mm-hmm. And do you guys kind of know how to start the baseline model and the saturated model? That honestly is a little advanced, okay? So, but I hope you can derive it from the slides I looked at. You can go back to the baseline slide and the saturated slide. Remember, the baseline is everything without the covariance, and the saturated is everything with the covariance. So fit the covariance model. Right? The hint is you need all the variances and covariances in the saturated model, and then you can use the plus operator to add multiple covariances in one line. So that's the hint. So the key operator here is the double tilde, right? You need the double tilde to fit all these. So you need double tildes and then you need plus. And that's pretty much all you need to fit these models. And then you just need a calculator to calculate the CFI. You can also type it into R and let R calculate it for you. Okay, so don't worry if you didn't finish. But okay. So you can see the answer is already there. What did you guys get? Did anyone get the CFI? Oops, I think I closed the window. Oh, 0.8, yeah, okay. Did anyone else get like 0.869 or 0.87? And that should match the, sorry, I'm sharing my screen. That should match the first model, right? Let's see. I don't even remember what I did. No, I think it was something else. What? No, it's the one where you have all 8, right? Which one? Where did I put that? Yeah, the one where we have all 8. No, what did I do wrong? 1, 2, 3, 4, 5, 6, 7. Oh, I copied this wrong. Yeah, I think it's probably rounding error too. Let me just make sure. Yeah, I think it's rounding error. Okay, so anyone want to share how they did it? It should be around 0.87, right? Okay. So the baseline model was directly from the web page. Basically, you want to make sure you get all the variances, right? And no covariances, right? By default, it doesn't estimate the covariances. So what you want to do is then just say, item 1 with item 1, and then just do that for all the items, okay? So that's how you do the baseline model. And then you should get, so So you look at the model test user model, right? So you don't look at the other one because that is but you can verify that that is the baseline model. So then you should get a test statistic of 4164 and then a degree of freedom of 28. Now, how did you fit the saturated model? Well, basically it's the variances plus the covariances, right? So then I basically add the variances here. I copy that. And now I add the covariances. And basically you don't want to duplicate them, right? So you want like 1 with 2, 3, 4, 5, 6, 7, 8, 2 with 3, 4, 5, 6, 7, 8, etc. until Q7 with Q8. And that's what I meant. You can now simplify it by adding. So that estimates the covariances. So you basically have the variances and covariances. And then that's the saturated model. And you know that because the degree of freedom is 0. Now, which one do you use this one for the CFI? No, I'm just demonstrating this for purposes of demonstration. Now, what I think you should get, and correct me if I'm wrong, is I think you should use the model test here, right? 554, and then degree of freedom is 20. And then you can verify that this is the same as that baseline model here in the test baseline. Okay, so if you subtract that from 20 and then you subtract this from 28, and then you follow the formula, you should be getting the CFI. Okay, so let me know if you guys get something else. But here's the answer. Okay. All right, so I think that's a good time to stop. But thank you all for participating. You guys were excellent participants. One of the best audiences I've had, and you guys looked like you were participating and engaged throughout the whole seminar. So thank you for that. And I hope you found that helpful. If you are interested in like a more advanced CFA seminar, like let me know, or like a SCM seminar that's more advanced, let me know. Otherwise, this is the conclusion of the seminar, and then you are free to go, or you can just stay and ask questions about things you didn't understand, or just general questions about CFA. Okay, but thank you so much.